Imagine a technology that's so fundamental to how we make almost everything that we hardly even notice it anymore. It's kind of like the air conditioning in a building, maybe, always there making things work until something completely revolutionary comes along and changes the whole game. Today, we're going to dig into exactly that kind of massive shift. We're taking a deep dive into something called RLP technology. That's the repeating layer process. And look, this isn't just some small tweak, making things a tiny bit faster or cheaper. No, this is positioned as a potential replacement for the assembly line, that cornerstone of manufacturing that's been dominant for over 120 years?
That's right, a really long time. And it's crucial to get this framing right from the start. RLP isn't just tweaking the old system. It's being presented as a totally new manufacturing platform. This came out of more than 4 years of really intensive development. They weren't just trying to optimize the assembly line, they were building something fundamentally different. It really is a paradigm shift.
Okay, let's unpack that a bit then. The assembly line. Since, the early 1900s, Henry Ford and all that, it's been the way things get made, right? Cars, phones, electronics, even, packaged food. It all moves down a line, step by step, sequentially.
It was revolutionary for its time. A true marvel.
And yeah, sure, we've bolted on loads of cool tech over the years to make it better. You've got SCADA systems, MES, ERP software managing everything.
Right, and conveyors, PLCs, HMIs controlling the machines.
Advanced robotics doing complex tasks, vision systems for quality checks, IIoT connecting everything, even digital twins simulating it all.
Absolutely. Tons of innovation. But here's the key point you touched on. All those technologies, brilliant as they are, they're built around that fundamental sequential model. They make the line smarter, faster, more efficient, but they don't change the core fact that it's still one step after another.
They manage the sequence, they don't replace it.
Precisely. And that core sequential model is the inherent limitation. Because each step has to wait for the one before it, you get bottlenecks. It fundamentally limits how much you can scale up, how high you can push the overall performance. You just can't escape that dependency.
Right. There's always a slowest step dictating the pace.
Exactly. And if you look at the typical benchmarks for a traditional assembly line, you see those limits clearly. First off, they're basically non-scalable in an exponential way. You can make the line longer, maybe faster, but you hit diminishing returns. Your operational equipment effectiveness, OEE, which is a key metric for performance, usually tops out around 85%. That's good, but not perfect.
85% sounds pretty good, though.
It is good, but that missing 15% represents waste downtime, defects, slow cycles, and then there's the physical side. They require, let's call it 100% footprint for a given capacity, a lot of space. That means 100% capital investment to build it, 100% operational cost to run it day to day, and ultimately 100% manufacturing cost per unit, which we'll use as our baseline for comparison.
Okay, so it's efficient up to a point, but inherently limited in scalability and has significant fixed costs.
Right. And that leads to the big question. If we've pretty much maxed out optimizing this century-old sequential model, how do we actually break free from those built-in constraints?
And I guess that's the cue for RLP technology. You're positioning it as the solution, this new manufacturing platform, RLP, repeating layer process. You said it's based on an innovative mathematical algorithm.
That's the core engine, yes.
And the big differentiator, the absolute game changer, is that it uses a parallel model instead of that sequential one.
Exactly. Parallel versus sequential. That shift sounds simple, maybe, but it's the key that unlocks everything else.
How so? What does shifting to parallel actually do?
Well, it fundamentally re-architects the whole process. Think about it. Instead of one long chain, you have multiple processes happening simultaneously, layered on top of each other almost. And when you compare the advantages directly to the assembly line, the difference is pretty staggering.
Okay, give us the numbers.
Right. So, model. Parallel versus sequential. We covered that. Scalability. A assembly line is non-scalable exponentially. RLP. It's demonstrably over 20 times more scalable.
20 times?
Over 20 times, yeah. In terms of capacity, increased potential, efficiency, that OEE number. Instead of 85%, RLP operates in the 92% to 99% range.
Wow, okay, that's a huge jump in uptime and quality output.
Massive. Then footprint. Instead of 100% space, RLP systems typically need only 25%. Less than half the physical area for the initial capacity, and even less relatively as you scale.
Quarter of the space. That saves huge amounts on real estate alone.
Absolutely. And that feeds into cost, capital investment, down to 50% compared to traditional for the same initial output and much less for scale output. Operational cost, also down to 50%. And the big one, manufacturing cost per unit, can be driven down to 50% or even less compared to the traditional baseline.
Half the cost per item produced.
Potentially, yes, once scaled. It's all managed by the RLP controller. Think of it as the brain.
Okay, this is sounding almost too good to be true. Half the cost, quarter the space, 20x scalability. Let's make it concrete. This mathematical algorithm, this parallel model, how does it actually work in practice? Can you walk us through an example? Maybe that battery module you mentioned.
Sure, the battery module is a great example because it clearly has repeating parts.
Okay, so set the scene. We're making a battery module, say for an EV. It's got 24 cells inside.
Yep, let's say 24 cells total. 12 positive, 12 negative. Those are our repeating layer components. They get added again and again.
Right, layers of cells.
Exactly. And you've got components like the outer case, maybe a cooling plate, the main electrical connectors, the bus bars. Those are non-repeating or overhead layer components. They typically only go in once per module.
Got it. Repeating cells, non-repeating case and stuff.
Now, for this system, let's say the RLP system's core cycle time, its heartbeat, needs to introduce one cell every 4 seconds.
4 seconds per cell introduction.
And system availability, that OEE, we use 95% for our calculations, though it ranges from 92% to 99%. And it runs, say, 21 hours a day, 240 days a year. Standard stuff.
Okay.
Now, calculating the total time to make one module involves those 3 parameters, remember. Green, blue, and yellow.
Refresh my memory.
Sure. Green is the total number of repeating layers needed. In our case, we need 12 positive and 12 negative cells layered in, so that's 12 repeating layers total for the purpose of this calculation pathway.
Okay, green equals 12.
Blue is how many layers get introduced in one pass or cycle around the RLP system.
For our basic starting point, let's say it's just 1 layer per pass.
Blue, 1. Makes sense.
And yellow is that RLP cycle time, the 4 seconds it takes to add that layer.
Yellow, 4 seconds. Got it.
So the formula is basically green, blue, yellow. How many passes needed times time per pass? Right, so 12 layers needed 1 layer per pass, 4 seconds per pass.
Exactly.
That's 12 passes times 4 seconds, 48 seconds. It takes 48 seconds to complete one module in this basic setup.
Correct. And if you calculate that out over an hour, that comes out to roughly 75 modules per hour.
75 modules an hour. Okay. How does that compare to a traditional line?
Well, here's the crucial part for this initial build level 1. At this stage, the manufacturing cost per unit is essentially the same as a traditional system designed for the same output. 100% baseline cost.
Ah, okay, so it doesn't start cheaper.
Not initially. The magic isn't just in the base unit, it's in the scaling. This is where RLP fundamentally diverges from the assembly line.
This is where the parallel part really kicks in, I guess. How do you scale it? You mentioned adding layers of machines.
Precisely. Instead of just making a linear line longer or adding more identical lines side by side, RLP scales by adding integrated layers within the system. Think vertically, almost, or in parallel tracks.
Okay, intriguing. Walk me through these build levels.
All right, so build level 1, that's our baseline, 1 layer of RLP machines. Produces 75 modules an hour. Cost is 100% compared to traditional standard stuff.
Got it.
Now, build level 2. Here's where it gets interesting. You don't add a whole new system, you add just 2 more machines, which might only be, say, 40% of the original system's cost and footprint.
Only 40% additional investment?
Roughly, yeah. But because of the parallel architecture, adding those machines effectively creates 2 processing layers. And what happens to output? It doubles. Goes up to 150 modules per hour.
Wow. Double the output for only 40% more cost.
Exactly. 100% increase in capacity. And the cost per unit, it drops significantly. Now it's down to 70% of what the traditional method would cost.
70%, just by adding those 2 machines intelligently. Okay, that's impressive. What's next?
Keep going. Build level 3. Add 2 more machines. Another 40% system cost increment. Now you have 3 layers of RLP machines working in parallel. Output increases again, proportionally. Now you're at 225 modules per hour. That's triple the original baseline capacity.
Triple the output for what, 80% total additional cost over the baseline?
Correct. And the manufacturing cost per unit drops again, now down to 60% of the traditional cost.
60%. Okay, I'm starting to see the power curve here. It's not linear growth at all.
Not even close. It's exponential gains through parallel processing. Let's do one more big jump. Build level 4, add another 40% of system components. 4 layers of machines now. Output hits 300 modules per hour. That's 400% of the initial system capacity, 4 times the output.
4 times the output. And the cost.
Manufacturing cost per unit is now down to 55% of traditional
Okay, hold on. So for roughly, what, 120% additional cost compared to the base level 1 system, you've quadrupled the output and cut the unit cost almost in half.
That's the principle, yes, and it continues. Let's jump to build level 6. Add 2 more layers of machines, now you have 6 layers humming along. Production capacity, 450 modules per hour. That is 600% of the initial system capacity, 6 times the output.
6 times.
For maybe 200% additional cost over the baseline system. And the manufacturing cost per module, it hits the target. 50% of the original cost. Half the cost compared to a traditional line designed for that initial 75 output.
That is fundamentally different. So, summarizing this for the listener, RLP isn't just about a baseline efficiency, it's about this incredible ability to scale. You can get 6 times the production output, hitting 450 units an hour in this case, while simultaneously driving the cost per unit down to half of what it would be traditionally. And you achieve this not by building 6 separate lines, but by adding maybe only double the initial investment into the same system footprint area, leveraging that parallel layered approach.
You got it. That's the core takeaway. Massive capacity increase, dramatic cost reduction per unit, all achieved with relatively small incremental investments by adding parallel layers, not just linear extensions.
Okay, stepping back then, what are the broader implications of this? If companies can actually achieve this kind of performance, what does it mean?
Well, if we connect these dots, RLP isn't just a better machine. It sets entirely new manufacturing standards and unlocks huge strategic advantages. Think about the benchmarks again. Production capacity scalable over 20x. Availability, that OEE, sustained between 92% and 99%. Cost per unit potentially under 50% of traditional methods. Real estate needed is less than half, maybe even a quarter when scaled. And time to market for products can be slashed because you can ramp up production so much faster.
Those are game-changing metrics across the board.
They are, and they translate into profound strategic advantages, especially when you think on a national or even global scale. First, adopting this kind of tech positions a nation as a leader in advanced manufacturing. It signals technological superiority.
Right, it's a capability advantage.
Second, it drives economic growth by creating high-tech manufacturing jobs.
Yeah.
These aren't just assembly line jobs, they're jobs managing sophisticated data-driven systems. Third, global competitiveness. If your nation's companies can produce critical goods at half the cost and twice the speed, you gain significant market dominance.
You can basically outcompete purely on production efficiency.
Fourth, it fosters an innovation hub. Success attracts investment, R&D, talent. It creates a virtuous cycle. Fifth, and this is really critical today, it supports essential infrastructure and supply chains. Think EV batteries, semiconductors, solar panels, pharmaceuticals. Being able to make these reliably and cheaply onshore is huge.
Yeah, resilience and supply chain security are massive issues right now.
Absolutely. Which leads to the final point, strategic autonomy. It gives a nation much greater control over its essential manufacturing capabilities, reducing reliance on potentially unstable global supply chains.
So this really elevates manufacturing. It's not just about, widgets per hour anymore. It becomes a tool for economic strategy, national security, global influence.
That's exactly the perspective. It's a fundamental shift in capability.
Okay. So we've really dug deep today into RLP technology, this repeating layer process. We've looked at how its parallel model aims to replace the century-old sequential assembly line, its frankly staggering scalability, and the potential for dramatic cost reductions.
Yeah, and I think the real aha moment, or the thing to grasp, is that RLP isn't just making the old line better. It's a totally different way of thinking about production. That parallel layered approach fundamentally changes the math, the economics, the possibilities of manufacturing.
It really does seem to flip the script. So a final thought for you, our listener. What stands out to you most about RLP? As you look around at the complex products that fill our lives, your phone, maybe parts of your car, future tech like advanced batteries, how might this kind of fundamental shift in how they're made impact their visibility, their cost, or maybe even their design in the years ahead? It's definitely something to think about, the ripple effects when a foundational technology truly changes.